Right now, space itself stretches at unimaginable speeds, dragging galaxies apart faster than the speed of light. That sentence alone sounds like science fiction, yet it's one of the strangest truths in all of physics. The empty darkness between galaxies isn't just sitting there like a static backdrop. It's alive, dynamic, and constantly growing. Every second, the scale of the universe changes, as if reality itself were breathing, expanding into nothing at all. And that word nothing is where the mystery begins. Because when we ask what the universe expands into, the unsettling answer is absolutely nowhere. There is no outside, no void waiting to be filled. Space grows within itself, stretching distances, bending light, carrying stars and galaxies like passengers on an invisible current. You live inside this bizarre process every single moment, though you can't feel it happening. The ground beneath your feet seems solid and unchanging, yet the universe has been reshaping around you since the instant time itself began. Think about it. The nearest star to our sun is over 4 light-years away, a gulf so vast that even at light speed, it would take more than 4 years to reach. That distance is not fixed, it's growing right now. Between galaxy clusters, separated by millions of light-years, expansion is unstoppable. The space between them is stretching, dragging the galaxies farther and farther apart. The sheer scale defies the human mind. A region of space 1 million light-years wide grows by more than 20 meters every second, a relentless swelling that reshapes the cosmic landscape. When scientists first discovered this expansion, they were stunned. Everything we see, every speck of matter, every galaxy was once closer together. If you reverse the process, all of it collapses back into a single, unimaginably small point, a singular moment of origin we call the Big Bang. And yet, the Big Bang itself wasn't really an explosion. Explosions happen in a pre-existing space, pushing debris outward. But the Big Bang created space itself. Time, matter, and energy were all born in that single instant, and from that moment on, the universe has never stopped growing. But here's the twist: the universe doesn't expand into anything else. It expands the way a balloon surface stretches as it's inflated. Imagine you're a tiny creature living on that balloon, unable to see above or below the surface. As the balloon inflates, every point on it moves away from every other point, and from your perspective, the entire world grows larger. Yet there's no outside that matters to you, no direction you can point and say, that's where space is going. That's our reality, except on a far greater scale and with more dimensions than we can perceive. We are embedded in 3-dimensional space that swells without requiring an external container. Expansion is intrinsic. It's not pushing into emptiness, it's creating more space as it grows. This single fact has consequences so bizarre that it shatters our common sense. It means there is no center of the universe, no special location where expansion began. From Earth, it looks like all galaxies are racing away from us, as though we sit at the very heart of creation. But the same is true from every other galaxy's point of view. Every observer in every galaxy sees themselves at the center, even though no true center exists. Reality plays a trick on every civilization that looks out into the night sky. It convinces them that they are special, that they occupy the middle of everything. In truth, the universe has no middle, no edge, no outside at all. Just endless expansion into itself. And as strange as this sounds, the story doesn't stop there. Because when astronomers studied this expansion more closely, they discovered something even more terrifying, something that suggests the universe's fate may be far darker, lonelier, and more mysterious than anyone imagined. When most people hear the word space, they picture an empty void, a silent nothingness stretching endlessly in all directions. But the deeper science digs, the clearer it becomes that space is anything but empty. It isn't a passive backdrop where the drama of stars and galaxies plays out. It's the main actor, a restless stage that bends, stretches, vibrates, and even grows larger as time passes. This may sound like poetic exaggeration, but it is the most literal truth we have. Einstein's general theory of relativity revealed over a century ago that space is not just a vacuum. It has structure, it has geometry, and it responds to mass and energy. Drop a heavy ball on a trampoline and watch the surface bend inward. That curve represents what happens to space whenever matter exists within it. Stars and planets don't pull objects by some invisible force the way people once thought. Instead, they bend the very fabric of space, and smaller objects simply follow those curves, like marbles rolling toward the ball on the trampoline. Gravity isn't a force in the old Newtonian sense, it's the shape of space itself. But here's the part that twists the brain. Space doesn't just bend, it stretches. Even in regions where no stars, no planets, and no light exist, the fabric of space itself grows. Imagine drawing a grid on a balloon with a marker. As the balloon inflates, every square in the grid gets larger. Every line stretches farther apart. Nothing is moving across the balloon's surface. The surface itself is expanding. That's how the universe works. Except instead of a rubber sheet, it's three-dimensional space itself, and instead of air filling it from the outside, the expansion is intrinsic, built into the way reality behaves. There is no outside pressure, no cosmic air pump. Space simply creates more of itself as time moves forward. This realization alone shattered the old picture of a static universe. For centuries, philosophers and scientists assumed the cosmos was eternal and unchanging. Even Einstein, when his own equations predict expansion, added a fudge factor to keep everything fixed. He couldn't accept the idea that space itself was alive with growth. Only when Edwin Hubble measured the redshifts of distant galaxies did the truth become undeniable. The universe is expanding everywhere, all at once. And here's where it gets even weirder. The expansion doesn't require galaxies to fly through space like rockets. Instead, space itself stretches, carrying them apart. Galaxies remain almost motionless relative to their local region of space, but the ground beneath them, the very fabric of the cosmos, grows, and with it, distances increase. This is why some galaxies appear to recede faster than light itself. At first glance, that sounds like a violation of Einstein's ultimate speed limit. But relativity only forbids matter from traveling faster than light through space. It says nothing about how fast space itself can grow. Expansion doesn't push galaxies like wind pushes a sail. It carries them along like raisins embedded in dough as it rises. The raisins don't move relative to the dough, yet the dough makes them farther apart over time. On the cosmic scale, space stretches faster than the photons racing through it, leaving vast regions of the universe forever beyond our view. The most mind-bending part is that this stretching doesn't stop anywhere. There is no boundary where expansion ends. On the largest scales, it happens uniformly across the universe, everywhere, in every direction. On small scales, between atoms, between planets, even between stars in a galaxy, other forces like electromagnetism and gravity overwhelm it, holding things together. But across the gulfs of millions of light years, nothing resists. Expansion wins, space grows, and galaxies drift apart endlessly. It means that the very measuring stick of reality is changing beneath our feet. A million light years today is not the same as a million light years tomorrow. Space is dynamic, restless, always shifting. And this truth raises another question, one that kept physicists awake for decades. If expansion is everywhere, why does it look like it's centered on us? Why does every galaxy see itself as the cosmic middle? The answer to that question is even stranger than the expansion itself, and it would force scientists to rethink everything they thought they knew about our place in the universe. In 1929, Edwin Hubble climbed into the dome of what was then the world's largest telescope and pointed it toward the stars, expecting to confirm what most scientists already believed, that the universe was calm, stable, and eternal. Instead, what he saw shattered that illusion forever. Through careful observation, Hubble noticed that the light from distant galaxies didn't arrive at Earth in the colors physics predicted. Instead, those familiar fingerprints of hydrogen and helium appeared stretched, shifted toward the red end of the spectrum. This phenomenon, which we now call redshift, was more than a curious anomaly. It was the signature of something unimaginable. It meant that those galaxies were racing away from us, and the farther away a galaxy was, the faster it seemed to be fleeing. Double the distance, double the speed. The relationship was so precise that it became a law. Hubble's law, the mathematical key that revealed our universe isn't static at all, it's expanding. The discovery was so shocking that even Albert Einstein, who had already stumbled across equations predicting expansion, admitted he hadn't believed them. To avoid such a possibility, he had introduced a correction term called the cosmological constant, a kind of mathematical patch that forced his equations to describe a universe that stood still. When Hubble's observations proved expansion was real, Einstein famously called the constant his greatest blunder. Yet what truly disturbed astronomers was not just that galaxies were moving apart, but the speeds at which this was happening. Hubble's measurements revealed galaxies millions of light years away tearing across the cosmos at hundreds of thousands of miles per hour. Push farther out, and some appeared to recede faster than light itself. This was no ordinary motion, it was the universe stretching beneath them. Imagine what this looked like to the scientists of the early 20th century. For centuries, humans assumed Earth sat at the center of everything. Copernicus removed us from that illusion by showing Earth orbits the Sun. Later discoveries proved the Sun was just one star in a galaxy among billions. But Hubble's revelation brought an even stranger twist. The universe itself was growing, and every galaxy appeared to be running away from us. At first glance, that seemed to put us back at the center. After all, if everything flees from our vantage point, doesn't that mean we're special again? But the math told a very different story. No matter where you stand in the universe, whether on Earth, in the Andromeda galaxy, or trillions of light years away, you see the same pattern. Everything else appears to be moving away from you. The expansion is universal, with no preferred point, no single location where it all began. This illusion of centrality rattled the scientific worldview. It meant the universe had no middle, no edge, and no boundary. Expansion was everywhere, all at once, and if you trace it back in time, as Hubble did, you realize something even more profound. If galaxies are racing apart today, then billions of years ago they must have been closer. Keep winding the cosmic clock backward, and everything converges on a single point, a time when space and matter were compressed into an unimaginably small, dense state. That backward journey leads us straight to the moment we now call the Big Bang, the origin of space and time itself. For scientists of the early 20th century, this was a paradigm shift of terrifying proportions. The universe wasn't eternal. It had a beginning. And if it had a beginning, then it must also have an end. The discovery that space itself expands not only destroyed the idea of a static universe, but raised unsettling questions about what, if anything, lies beyond the limits of our perception. Even stranger, if every galaxy sees itself as the center of expansion, what does that mean about our place in the cosmos? Could it be that every civilization, no matter where it exists, is tricked into believing it occupies the middle of reality? That unsettling thought led to one of the strangest conclusions in science. Expansion gives every observer the illusion of centrality, even though no true center exists. And if there is no center, then where exactly did the expansion begin? What did it expand into? These questions revealed a universe stranger than anyone had imagined, forcing scientists to abandon old models and search for a new understanding of what space, time, and reality really mean. But the answers they uncovered only deepened the mystery. Because the expansion wasn't just strange, it came with a hidden trick that makes every galaxy everywhere believe it sits at the heart of existence. Stand outside on a clear night and look up at the sky. To the naked eye, the stars appear motionless, eternal, scattered like jewels across an infinite black canvas. But hidden beneath that stillness is a secret so strange it feels almost like a cosmic trick. Every single galaxy we can observe seems to be fleeing from us, as though Earth itself sits at the very center of reality. This illusion, however, is not unique to us. If you were standing on a planet orbiting a star in the Andromeda galaxy, you would see the same thing, every other galaxy, in every direction, appearing to move away. Shift your perspective to a galaxy on the far edge of the observable universe, and the same pattern unfolds. Each point in space experiences itself as the center of expansion, even though no such center exists. This is one of the most counterintuitive and mind-bending aspects of our universe. Expansion makes every observer believe they occupy the middle of everything. To understand how this works, imagine once again the balloon analogy. Draw dozens of dots on the surface of an uninflated balloon. Each dot represents a galaxy. Now start blowing up the balloon. As the surface stretches, every dot moves away from every other dot. But notice something strange. If you pick one dot and focus only on it, it looks like every other dot is rushing away from that single location. Move your focus to a different dot, and the same things, every dot appears to be the center of expansion from its own perspective. The reality is that expansion has no single origin point on the surface. It is uniform, affecting every location equally. The balloon doesn't have a center on its surface because the center exists in a dimension you cannot access. Our three-dimensional universe works the same way. Expansion is intrinsic, not extrinsic. It doesn't need an outside to grow into. It simply happens everywhere, all at once. This is why no matter where an astronomer points a telescope, the same law applies. Galaxies farther away recede faster, and those closer appear to move more slowly. The redshift patterns confirm it with mathematical precision, and yet the illusion of centrality is so powerful that it feels impossible to accept. Human beings evolved in a world where everything has a center. A campfire has a center, a city has a center, even the Earth itself has a core. But the universe refuses to play by those rules. It operates on principles that defy our instincts. There is no cosmic capital, no privileged location, no edge where you could travel far enough to see the boundary of existence. If you journeyed in a straight line for billions of light years, you would never hit a wall. You would simply encounter more space, more galaxies, more expansion, as if the universe stretches endlessly without any need for an outside container. The unsettling truth is that the Big Bang didn't happen at one specific point in space. It happened everywhere at once. Space itself was born in that moment, and every single location we see today was compressed into that unimaginably small state. As the universe expanded, it carried all regions away from all others. This means that every place in the universe can claim to have been the site of the Big Bang, because in a very real sense, it was. The beginning didn't erupt from a central point and spread outward into a pre-existing void. Instead, space itself came into existence, expanding from within, creating distance where none had existed before. What makes this even stranger is how it warps our perception of time. When we look at distant galaxies, we aren't just seeing them far away, we're seeing them far back in history. Light takes time to travel, so a galaxy 10 billion light-years away shows us its appearance 10 billion years ago. But while that light was crossing the void, space continued to expand. The galaxy we observe as it once was is now much farther away than when its light first left. The expansion of space stretches not only distances but time itself, making the universe an ever-changing tapestry that no observer can ever fully grasp. And here lies the paradox. The universe has no center, yet from every galaxy's perspective, it seems to sit right at the middle of the action. This illusion is not a bug in the system. It's built into the very nature of expansion. Every civilization that develops telescopes and begins to study the cosmos will be tricked into thinking they're special, that their galaxy occupies the center of everything. Only through mathematics and observation do we realize the truth. The universe has no preferred position, no unique vantage point. Expansion belongs to everyone equally. But if the universe expands everywhere at once, carrying all galaxies away from one another, that raises a haunting question. How far can this expansion go? Does it stretch forever, endlessly carrying galaxies beyond our reach? Or does it have limits, boundaries we simply haven't yet discovered? The answer would reveal not only the fate of distant galaxies, but the ultimate destiny of the universe itself. When Edwin Hubble first revealed that galaxies were receding, it was already a shocking revelation. But hidden within his data was an even more disturbing truth, one that continues to haunt cosmologists today. Many galaxies aren't just moving away, they're doing so at speeds that defy our most fundamental understanding of physics. Some galaxies appear to recede faster than the speed of light itself. At first glance, this seems impossible. Einstein's special relativity carved into the foundation of modern science the rule that nothing with mass can travel faster than 6,000 miles per second. Break that law, and you might as well throw out physics altogether. But the key lies in recognizing the subtle difference between moving through space and being carried by the expansion of space itself. Imagine two ants crawling across the surface of a balloon as it inflates. Each ant moves slowly, step by step, across the rubber. But as the balloon grows, the distance between them increases faster than either ant could ever crawl. The ants are not breaking any speed limit. They're simply passengers on a stretching surface. Galaxies work the same way. They aren't rocketing through space at impossible velocities. They're relatively stationary in their local regions, while the cosmic fabric between them expands. This is how a galaxy 14 billion light-years away can recede faster than light without ever violating Einstein's speed limit. The rule applies to motion through space, not to the growth of space itself. This distinction may sound technical, but its consequences are profound. It means there are galaxies we can see now because their light left them billions of years ago, but we will never see them again, even as their ancient light finally arrives at Earth. Expansion is carrying them away faster than light can close the gap. Eventually they cross a cosmic horizon, a boundary beyond which no signal, no photon, no information of any kind can ever reach us. They vanish not because they stop existing, but because expansion pulls them into a realm forever beyond our perception. This horizon creates a kind of cosmic prison. Our observable universe, roughly 46 billion light-years in radius, is not the whole universe. It's simply the part that expansion still allows us to see. Beyond it may lie infinite galaxies, infinite stars, even infinite versions of ourselves, but they are permanently out of reach. The realization that expansion can outpace light is one of the most mind-bending ideas in cosmology. It challenges the way we think about distance, speed, and reality itself. Light, which we usually treat as the ultimate messenger, the fastest carrier of information, is powerless against the relentless stretching of space. The most distant galaxies send us their light, but that light arrives redshifted, stretched to longer and longer wavelength by the very expansion it travels through. Blue light becomes red. Red turns to infrared, infrared to microwave, until the photons fade into background whispers of energy. Expansion doesn't just carry galaxies away, it stretches the messages they send, diluting them into near nothingness. For astronomers, this creates a haunting irony. The deeper we peer into the cosmos with powerful instruments like the Hubble Space Telescope or the James Webb Space Telescope, the more we see of the early universe. We capture ancient light from galaxies as they existed billions of years ago, but at the same time, those galaxies are now farther away than light can ever reach. It's like receiving a postcard from a friend, only to learn that while the letter was traveling, they moved to a place you can never visit again. We glimpse their past but lose their future. This leads to a sobering conclusion about our cosmic fate. As expansion continues, more and more galaxies will cross that horizon. The observable universe will shrink, not in physical size, but in terms of what it contains. Today, we can see roughly 2 trillion galaxies. In the far future, that number will dwindle as distant clusters slip away into invisibility, leaving only our local group of galaxies, Milky Way, Andromeda, and a few smaller companions gravitationally bound together. Billions of years from now, the universe will appear empty, not because it is, but because expansion has erased the evidence from view. This reality forces us to confront a disturbing thought. If so much of the universe is already beyond reach, what secrets are we losing forever? Are there galaxies larger than anything we've seen, physics unlike our own, civilizations far older and more advanced? Expansion ensures we can never know. The laws of physics themselves impose a cosmic censorship, keeping vast portions of reality hidden behind an unreachable curtain. And just when scientists thought they were beginning to understand this strange behavior of the cosmos, an even more unsettling discovery emerged. Expansion isn't just happening, it's speeding up. For decades after Hubble's discovery, astronomers assumed the expansion of the universe would eventually slow down. The logic seemed inescapable. Gravity is the great cosmic anchor, pulling everything together. The collective mass of galaxies, stars, gas, and dark matter should gradually put the brakes on the expansion, just as a ball thrown into the air eventually slows under Earth's pull. The debate wasn't about whether the expansion would decelerate, but how. Would there be enough matter to reverse the expansion entirely, dragging everything back into a catastrophic big crunch? Or would the expansion continue forever, only at a slower and slower pace, until galaxies drifted apart into the dark? No one, not even the most daring theorists, imagined that the expansion might do something far stranger. But in the late 1990s, 2 independent teams studying distant supernovas stumbled upon evidence that turned the scientific world upside down. These supernovas weren't ordinary explosions. They were type-wire supernovas, stellar catastrophes, so uniform in brightness that astronomers treat them like cosmic yardsticks. By comparing their observed brightness with their known luminosity, scientists can calculate to precisely how far away they are. Combine that with redshift measurements, and you can map how the universe's expansion has changed over time. When researchers plotted the distances of these supernovas against their velocities, they expected to see a neat pattern. The farther back in time you look, the more the expansion should have slowed. Instead, they found the opposite. The distant supernovas were dimmer than expected, which meant they were farther away than any decelerating universe could explain. Somehow, expansion had sped up, pushing those galaxies to even greater distances than anticipated. The results were so shocking that many scientists initially doubted them. Surely there must be an error, miscalibrated instruments, flawed assumptions, overlooked variables. But both teams, working independently, reached the same conclusion. And as more data poured in from other observations, galaxy surveys, the cosmic microwave background, and gravitational lensing studies, the evidence became undeniable. The universe was not just expanding, it was accelerating. Something was overpowering gravity on the largest scales, pushing galaxies apart with ever-increasing speed. This mysterious force received a simple but haunting name: dark energy. Nobody knows what it is. It doesn't emit light, doesn't interact with matter in any detectable way, and seems to be spread uniformly throughout all of space. But its effects dominate the cosmos. Current measurements suggest dark energy accounts for roughly 68% of the total energy content of the universe, while dark matter makes up another 27%, leaving less than 5% for everything we actually see. Stars, planets, people, everything made of ordinary atoms. In other words, everything familiar is just a thin veneer on a reality ruled by invisible forces we barely understand. The discovery of dark energy raised terrifying questions. If expansion is accelerating, what does that mean for the future? One possibility is the so-called heat death, where galaxies drift so far apart that stars eventually burn out, black holes evaporate, and the universe fades into a cold, dark void. Another, more violent scenario is the Big Rip, where dark energy grows stronger and stronger until it tears apart galaxies, stars, planets, and eventually even the atoms themselves. Alternatively, dark energy might not be constant. It could evolve over time, weakening or even reversing, leading to a future collapse. Each possibility paints a very different ending for everything we know. And right now, no one can say for certain which one awaits us. What makes dark energy especially disturbing is how little we can say about it. The best theories of physics, general relativity, quantum field theory, offer explanations, but none fit the data cleanly. Some suggest dark energy is simply the energy of empty space, a cosmological constant Einstein once introduced and later discarded. Others propose exotic new fields or even interactions with hidden dimensions. A few argue that our entire understanding of gravity may need revision. Whatever the case, dark energy is more than just an astronomical curiosity. It is the single biggest factor shaping the destiny of the universe. The discovery of accelerating expansion earned its discoverers the Nobel Prize in Physics, but the prize came with an unsettling realization: the universe is stranger and more unpredictable than we ever imagined. Expansion doesn't just carry galaxies apart. It does so with increasing urgency, as if driven by a force that lies beyond the reach of our deepest equations. And yet, this revelation was only the beginning, because once scientists accepted dark energy's existence, they faced an even more chilling mystery. Why did its dominance begin only recently, around 5 billion years ago? Why not sooner or later? Why now, at the precise moment when intelligent beings happen to exist and notice it? This so-called cosmic coincidence problem is one of the greatest puzzles in modern science. It suggests either a bizarre accident of timing or some deeper principle of reality we have yet to uncover. Whatever the truth, the message is clear. The universe is not winding down in some predictable, orderly fashion. Instead, it is being propelled toward a future dictated by a mysterious energy we cannot see, cannot touch, and cannot comprehend. And the deeper scientists dig, the more unsettling the story becomes, because dark energy isn't the only invisible actor shaping cosmic destiny. Another hidden player lurks in the shadows, weaving the very scaffolding of the universe. If dark energy rules the fate of the cosmos on the grandest scales, then dark matter is the silent architect shaping its structure. It is the invisible scaffolding upon which every galaxy, every cluster, and every filament of the cosmic web is built. Without it, the universe would be an unrecognizable void, a thin mist of gas too evenly spread out to ever clump into stars or planets. In fact, without dark matter, nothing resembling life could have emerged at all. What makes this even stranger is that while dark energy works by pushing everything apart, dark matter acts in the opposite way. It pulls. It has no light, no color, no interaction with electromagnetic forces, and yet its gravity is undeniable. Wherever astronomers look, the evidence for its presence piles up like a trail of invisible fingerprints. The first real clue came in the 1930s, when Fritz Zwicky observed galaxies moving within the Coma cluster. By his calculations, the galaxies were orbiting too fast to be held together by the visible matter in the cluster. They should have flown apart long ago, scattering into the emptiness of space, but they hadn't. Something unseen was providing the missing gravitational glue, outweighing the visible stars by factors of 10 or more. Astronomers were skeptical, and for decades the mystery was largely ignored. Then, in the 1970s, Vera Rubin confirmed the case with her study of spiral galaxies. She measured how fast stars rotated around the galactic center and discovered something shocking. Instead of slowing down in the outer regions as expected, stars on the edges moved just as quickly as those near the center. This made no sense if the only mass present was what we could see. The conclusion was unavoidable. Vast amounts of invisible matter must surround galaxies in enormous halos, extending far beyond the reach of their visible light. Today, the picture has only grown clearer. The cosmic microwave background, the afterglow of the Big Bang, shows tiny fluctuations in temperature that map the seeds of structure. Those patterns can only be explained if dark matter was present to amplify them, pulling ordinary matter into dense regions where galaxies would eventually ignite. Computer simulations confirm this. Start with a universe of only visible matter, and no structures form. Add dark matter, and a magnificent cosmic web emerges, filaments stretching across hundreds of millions of light years, connecting galaxy clusters like beads on invisible strings. Ordinary matter, the kind that makes up everything familiar, is just the frosting. Dark matter is the skeleton. Yet despite all this indirect evidence, the true nature of dark matter remains elusive. We know what it is not. It is not made of protons, neutrons, or electrons. It is not photons, neutrinos, or any particle in the standard model of physics. It does not clump into stars, does not ignite, does not scatter light. Instead, it slips silently through ordinary matter as if it were a ghost. Some theories suggest it could be exotic particles called WIMPs, weakly interacting massive particles that formed in the early universe and still linger everywhere today. Others propose axions, ultralight particles that ripple across the cosmos like invisible waves. A more radical idea is that dark matter might actually consist of primordial black holes, tiny remnants from the very first instance after the Big Bang. Each possibility would rewrite physics in its own way, but so far, experiments searching for dark matter particles have come up empty. What makes the mystery even more unsettling is the balance it strikes with dark energy. While dark energy pushes the universe apart, dark matter pulls it together. For billions of years, dark matter's gravity dominated, allowing galaxies and clusters to form and grow. Only about 5 billion years ago did dark energy take over, flipping the balance and accelerating expansion. This cosmic tug-of-war shapes not only the past, but the future of the universe. As dark energy grows stronger, it will eventually overwhelm dark matter, halting the growth of structure entirely. Galaxies will still exist, but no new ones will form. The great cosmic web will freeze in place, locked forever in its final pattern. For us, Dark matter is not just a curiosity, it is the reason galaxies like the Milky Way exist at all. Our sun, our planet, and our lives are possible only because dark matter's invisible hand gathered ordinary matter into clumps dense enough to ignite stars. Every breath you take depends on a force you cannot see, a substance that makes up more than 5 times the mass of everything familiar. And yet, for all its importance, it remains hidden, refusing to reveal its true face. Dark matter is the great paradox of modern science. It is simultaneously everywhere and nowhere, dominating reality while escaping direct detection. We measure its gravity, trace its influence, and map its distribution across the sky, but the particles themselves remain beyond our grasp. And just like dark energy, its mystery hints at physics far deeper than we currently understand. But the universe had one more shock in store, because with dark matter and dark energy accounted for, scientists uncovered a baffling inconsistency, a tension in the very rate of expansion itself, one that suggests something fundamental about our picture of the cosmos is deeply wrong. If dark matter and dark energy weren't enough to keep physicists awake at night, another problem has crept into the heart of cosmology, one that threatens to unravel everything we think we know about the universe. It's called the Hubble tension, and it began as a small discrepancy that many thought would be ironed out with better data. Instead, as observations grew more precise, the discrepancy grew sharper, stubbornly refusing to go away. Today, it stands as one of the greatest mysteries in modern science. The universe appears to have 2 different expansion rates, depending on how you measure it, and if both sets of measurements are correct, then something fundamental about our understanding of reality is missing. The story starts with Edwin Hubble in 1929. His discovery that galaxies are fleeing from us at speeds proportional to their distance gave birth to the idea of an expanding universe. That relationship is captured in a single number, the Hubble constant, which describes how fast space expands per unit of distance. For nearly a century, astronomers have worked to measure this constant with increasing precision, refining the techniques and calibrating the cosmic yardsticks. By the late 20th century, it seemed like just a matter of time before we would pin down the exact value. But instead of clarity, new observations opened a rift. One way to measure the expansion rate is to look at the early universe, specifically the cosmic microwave background, the faint afterglow left from when the universe was just 380,000 years old. Satellites like WMAP and Planck mapped this radiation with exquisite detail, revealing ripples and patterns that encode the density, composition, and geometry of the young cosmos. From those data, scientists can calculate how the universe should have expanded over time, leading to a predicted value of the Hubble constant about 67 kilometers per second per megaparsec. In other words, for every 3.26 million light-years of distance, galaxies should recede 67 kilometers per second faster. But when astronomers measured the local universe using Cepheid variable stars, supernovas, and other standard candles, they got a different answer. The local measurements consistently returned a higher value, about 73 kilometers per second per megaparsec. At first, the difference seemed small enough that statistical errors could explain it. But as telescopes improved, and as the James Webb Space Telescope added its astonishing precision, the disagreement became undeniable. The error bars shrank, yet the gap remained. 2 entirely independent methods, both incredibly precise, give answers that differ by nearly 9%. That difference might sound trivial, but in cosmology it's enormous, far too large to ignore. This Hubble tension poses a brutal question. Is our model of the universe incomplete? If the early universe measurements are correct, then the physics of the cosmos is deeply understood, but something in the local universe is fooling us. If the local measurements are correct, then the standard cosmological model, the very framework that explains dark matter, dark energy, and the Big Bang, may need revision. Either way, the discrepancy demands an explanation. Some scientists suggest that unknown particles may have existed in the early universe, subtly changing the way expansion unfolded. Others propose that dark energy is not constant, but evolves over time, accelerating the universe differently in the past than it does today. Still others argue that Einstein's theory of gravity itself might need modification, a possibility that makes even the most daring physicists uneasy. The James Webb Space Telescope was expected to resolve the tension by clarifying Cepheid star measurements and ruling out possible errors. Instead, it confirmed the local measurements with breathtaking accuracy. Every independent technique, Cepheids, red giant stars, supernovas, converged on the higher value. Meanwhile, the cosmic microwave background analyses remain rock solid, consistently pointing to the lower value. The contradiction refuses to budge. What began as a technical nuisance has evolved into a cosmic crisis. For now, the Hubble tension is not just a puzzle but a signpost. It points toward new physics waiting to be discovered, perhaps beyond the standard model, beyond our current grasp of space and time. It suggests that the universe still holds secrets we cannot yet imagine, and that our neat picture of cosmic expansion is far messier than textbooks would have us believe. And if history is any guide, these kinds of tensions often precede revolutions in science. When the orbit of Mercury didn't match Newton's predictions, it hinted at something deeper, eventually leading to Einstein's general relativity. Perhaps the Hubble tension is a modern echo of that kind of breakthrough, whispering that reality is stranger than our equations allow. But while scientists wrestle with the implications, the rest of us are left with a humbling thought. The universe is expanding, but we can't even agree on how fast. The very number that defines the tempo of cosmic growth is fractured, split between two answers that both appear true. Somewhere in that contradiction lies the next great leap in understanding, but until then, we stand at the edge of knowledge, staring into the abyss of uncertainty. And as unsettling as that sounds, it's only the beginning of the deeper mysteries that expansion hides. Mysteries about the very geometry of space itself. When we look out into the cosmos, we aren't just measuring distances and counting galaxies. We're also probing something deeper, the very shape of reality. Space itself, the fabric in which everything is woven, can curve, bend, and twist in ways that are almost impossible to imagine. And the shape of the universe isn't some idle curiosity. It decides the ultimate fate of everything. Is the universe flat, infinite, and destined to expand forever? Is it closed, curved back on itself like a sphere, doomed to one day collapse in a fiery crunch? Or is it open, shaped like a saddle, expanding without end into a future so cold and empty that nothing survives? For decades, cosmologists have wrestled with these possibilities, and astonishingly, the answer seems to balance on the sharpest of knives' edges. In Einstein's general relativity, matter and energy don't just exist inside space, they determine how space is curved. Every atom, every star, every galaxy contributes to the geometry of the cosmos. Too much mass, and the universe curves inward like the surface of a sphere, pulling everything back into itself. Too little, and the universe bends outward like a saddle, with expansion accelerating endlessly. But there exists one razor-thin threshold, called the critical density, where space appears perfectly flat. This doesn't mean flat, like a piece of paper, but flat in the mathematical sense. Parallel lines never meet. Triangles always add up to 180 degrees, and space extends forever without folding back or flaring outward. For years, scientists assumed the universe must be curved one way or another. Yet when they measured the cosmic microwave background, the ancient afterglow of the Big Bang, they discovered something astonishing. The temperature fluctuations across the sky lined up almost perfectly with what a flat universe would predict. Not slightly curved, not noticeably distorted, flat to within 1%. In other words, on the largest scales we can see, the universe seems to stretch out endlessly in every direction, balanced so precisely that it almost defies logic. Why should the universe hover so perfectly on the edge between collapse and runaway expansion? Why not tip one way or the other? Some believe the answer lies in cosmic inflation, that mind-bending moment in the first fraction of a second after the Big Bang, when the universe expanded faster than light. Inflation would have stretched any curvature so wide that the universe would appear flat to any observer, just as a balloon inflated to enormous size seems flat to the ants crawling on its surface. This solves the puzzle, but it raises another. What caused inflation, and why did it stop? These are questions physics still can't answer. Even more confusing is the role of dark energy. In a purely flat universe without dark energy, expansion should gradually slow, asymptotically approaching zero without ever reversing. But our universe is not playing by those rules. Dark energy accelerates expansion, bending the destiny of a flat cosmos toward an eternal cold emptiness. The geometry may be flat, but the fate is anything but calm. In fact, if dark energy grows stronger over time, it could even rip the universe apart, atom by atom, in a future big rip, where not just galaxies but stars, planets, and eventually the molecules in your body are torn asunder by expanding space. So what are we left with? A universe that looks flat, but only because something unknown has forced it into balance. A cosmos where geometry, density, and expansion are locked in a cosmic tug-of-war, where the difference between everything existing forever and everything collapsing into nothing comes down to 6 protons worth of matter in every cubic yard of space. That is the kind of razor-thin balance on which all of existence rests. And if that doesn't shake your sense of reality, consider this. Some physicists now believe the explanation doesn't lie in our universe at all, but in the possibility of many universes. Perhaps ours just happens to be the one where the balance was right, not by design, but by chance, because in an infinite multiverse, every possibility exists somewhere. And if that's true, then the question of geometry isn't just about this universe's fate. It's about whether there are countless others, each with their own shapes, their own destinies, and their own strange versions of reality. But before we leap into the multiverse, cosmologists have already proposed radical new ideas to explain the cosmic acceleration that geometry alone can't. Ideas so strange that they challenge the very concept of space as we know it. After all the mathematics, the measurements, and the theories, we're left with a truth so strange it almost feels like science fiction. The universe is not still. It is alive with motion. Not because stars and galaxies are flying apart through empty space, but because the stage itself, the very fabric of space and time, is stretching beneath them. This expansion is not something happening at the edge, pushing outward into a void. It is happening everywhere, in every direction, in every corner of reality, including the space between the atoms in your body. You don't feel it because gravity and electromagnetism bind you together, but it's there, a relentless stretching that began 13.8 billion years ago and shows no signs of stopping. We have learned that this expansion is not steady. It began in a violent eruption of inflation, slowed under the pull of gravity, and then 5 billion years ago picked up speed again under the mysterious push of dark energy. It has carried galaxies beyond our cosmic horizon, locking them forever out of view, and it will continue to do so until the universe we see today becomes a faint memory. In the far future, Trillions of galaxies will vanish from sight, leaving only our local cluster stranded in a sea of infinite blackness. The cosmos will grow emptier, colder, and darker with every passing eon. And yet, in this endless expansion, we have found profound mysteries. The Hubble tension tells us that two methods of measuring the universe's growth produce different answers, forcing us to admit that something fundamental is missing from our understanding. Dark matter, invisible and untouchable, shapes the skeleton of cosmic structure, while dark energy, an even more mysterious force, determines the fate of everything. Together, these unseen components make up 95% of existence, leaving us to grasp at only 5%, the part we call normal matter. We live our entire lives within a tiny minority of reality, surrounded and ruled by phenomena we cannot explain. But perhaps the most unsettling idea is that the universe may not be the only universe. Inflation predicts endless creation, an eternal bubbling of space-time spawning pocket realities, each with its own rules, its own shapes, its own destinies. Our flat, expanding cosmos could just be one island in an infinite ocean of universes, some expanding faster, some collapsing, some never forming stars at all. If that's true, then the balance of forces that allows us to exist may not be special at all. It may simply be one possibility among infinite others. And somewhere, perhaps unimaginably far beyond our horizon, other versions of reality unfold, forever hidden from us, forever unreachable. So what does this all mean for us, here and now? It means that we live in the rarest moment of cosmic history, a time when stars still shine, galaxies still cluster, and the night sky still reveals the evidence of a universe born in fire. Billions of years from now, future civilizations may never know what we see today. They may live under dark skies, unaware that trillions of galaxies once filled the heavens, blind to the truth of cosmic expansion because the evidence will have slipped forever beyond the horizon. We, by sheer chance of timing, exist in the only era when the universe reveals its secrets so clearly. Perhaps the greatest revelation is this: you are not separate from the expansion. You are part of it. Every atom in your body, every photon that reaches your eyes, every breath you take, happens against the backdrop of a universe that grows larger with every second. You exist not outside of this cosmic drama, but within it, carried forward on the tide of expansion, just like every star, every galaxy, every grain of cosmic dust. And while the universe may end in silence, the fact that you are here now, able to question it, to imagine it, to understand even a fragment of it, that may be the most extraordinary phenomenon of all. The universe expands into nothing, yet it contains everything. And somehow, within that paradox, we have found meaning, perspective, and wonder. The story of expansion is not just about galaxies and equations. It is about us, about our fleeting moment of existence in a cosmos too vast to grasp. And maybe, just maybe, that realization is what the expanding universe has been trying to show us all along.